We have seen Simon's problem last time. If you remember, we also saw an interpretation of it. The interpretation was that we were a hidden subgroup of the group Z2 to the K, and we wanted to find this hidden subgroup. Notice that the hidden subgroup was of specific form. It was this subgroup. We presented the problem as though this shift is hidden, but equivalently we can say that this H is hidden. And what were we given? We were given an oracle which was constant on cosets of H. This was one more interpretation of Simon's problem, and we saw that quantum computer can solve it successfully in log n queries. On the other hand, if we want to do it on a classical computer, it will take exponentially many queries. Today, we want to generalize this algorithm. What do I mean by that? We only know it for the group this. The generalization basically says that we can solve the hidden subgroup problem on any general finite abelian group. I will use HSP for hidden subgroup problem, and the goal of generalization would be to we can solve hidden subgroup problem on any finite abelian group. I would like to emphasize these two conditions. This is what we know. When the group is finite and abelian, then we can solve HSP. For other groups, it's a very interesting problem, but for most of them, we don't know what the solution is. Another important thing here is Fourier transform. If you remember, we solved Simon's problem using Fourier transform. Specifically, Fourier transform over Z2 to the K. On the other hand, if you want to solve it for a general finite abelian group, say G, then we should need a Fourier transform for G. That means the algorithm we want to generalize, or what we want to say is that we will use Fourier transform over a finite abelian group G. This will imply that we can solve the hidden subgroup problem over G. This is the exact statement we are going to see today. Using the Fourier transform of a finite abelian group G, we will solve HSP over G. You might ask, in what cases can we make Fourier transform over finite abelian group G? It turns out for all of them actually. Let me just specify. I'm not going to give the proof, but I'm going to just give you the idea. We have seen Fourier transform over Z2. We also saw Fourier transform over Z2 to the power n. This is something we did in class. At that point, I mentioned that we can even do DFT. This is the discrete Fourier transform. Not just that, we can do this by using DFT to the power k. Remember that this we did when n was equal to some power of 2. But we can even do it for other n's by similar techniques, and this was emphasized in Andrew Child's course notes. This reference is given in the course, in our course notes. You can look at that, and even this can be done using tensor product of TFT. For all these finite abelian groups, we know how to do Fourier transform. It turns out that any finite abelian group can be thought of as a product of these kind of groups. There's a fundamental theorem in mathematics, and this in some sense shows that we can do FT over any finite. Again, for details, you should refer to Andrew Child's course notes. I will not go into detail here, but the important to remember is that we can assume this too. If you saw the generalization, I said that if we have the Fourier transform over finite abelian G, we should be able to solve HSP over G. This is what we are going to see today, and the resulting discussion has told us is that this part can be assumed. We are not going to do this in the class, but this can also be assumed. Now, knowing this, let's look at how to generalize the hidden subgroup problem. So, we need to show given Ft over G implies we can solve HSP over G. But the first order is to ask what is HSP. I have hinted it multiple times. Let me formally define the hidden subgroup problem. For any group G, I can define a hidden group subgroup problem. For a given group G and a hidden subgroup H, suppose you are given an oracle, the oracle hides a function. What is the property of that function? You are given an oracle which is constant on the cosets of H. More importantly, it is distinct otherwise. That means the function gives a single value to a single coset. If given the access to such a function, can we find the hidden subgroup H? This is the hidden subgroup problem. Let me just emphasize the important things. Notice that H is hidden. We don't know what H is. What we have is an access to a function which is constant on cosets and different on different cosets. That means two elements have the same value if and only if they belong to the same coset. This is the critical property of the function. This is required to solve HSP. Knowing this, our goal or task is to find the hidden subgroup H. This problem is called hidden subgroup problem, and you might ask, why are we interested in HSP? There are many reasons for it. If you look at the basic problems, almost all of them are HSP problems. Simon's algorithm, Deutsch's problem, you will see that even Shor's algorithm is kind of a HSP problem. And then there are many HSP problems which we can't solve, but if we can solve them, we will solve interesting problems. For example, if you can solve HSP on dihedral subgroup, this will imply interesting solution for lattice problems, which are very important in cryptography. If you can solve HSP on symmetric group, notice that none of them are dihedral subgroup, symmetric group, both of them are not abelian. So we don't know how to solve them. But if you could solve them, this will imply a solution for graph isomorphism. I will remind you again, we don't know how to solve them. But if we can solve them, that would be great. This means two things. We know HSP algorithms for interesting problems. Many of the algorithms in quantum world are actually HSP algorithms. Secondly, if many other interesting problems are HSP problems. But in this case, they are on non-abelian groups. And we don't have the solution yet. We can solve it for finite abelian groups, but we don't have solution for HSP on non-abelian groups. If we can do that, we can solve many interesting problems. This is the reason why HSP has been hugely studied. There are so many papers and people have kept looking at HSPs. They have given bound that if you want to solve it, you will have to do this many queries, you have to devote this much time, so on and so on. So HSP is a really important problem. Now, I assume that you are convinced that HSP is a great problem. Then question is, can you solve HSP using quantum Fourier transform? First question would be, what is quantum Fourier transform? This is a reminder of what you have seen. I would like to remind you what is QFT. Remember that for any group, I can define functions which go from group to complex number such that chi of gh is equal to chi of g multiplied by chi of g. They respect the group multiplication, and the chi is actually a function which does not take value 0. They cannot take value 0. In this case, chi is called a character of h. I should say of g. Interestingly, in this case, everything has mod 1. Not just that, the total number of characters are equal to the size of the group. More importantly, if you look at these characters, guys, they form an orthonormal basis for all the functions which are living in this space. any function, I can write it as an element here and characters given orthonormal basis for this. This implies any f can be represented or written as a linear combination in terms of characters. This is essentially the Fourier transform. What is QFT? In this case, I will write out my function values as a vector. I can say f of g1, f of gn, normalize it somehow. I will leave this vector out, but this I can call f vector, and then applying the QFT, I should get the Fourier coefficients out. We have studied them. I hope this remainder is enough. Now we know that this is the transformation. Explicitly, I can describe Fourier transform over the basis vectors, which is going to be if you are confused about this, G hat is the group of characters. This is precisely the Fourier transform. Here I am notifying the action of Fourier transform on every group G. We know that size of G is same as size of G hat. I advise you to look at this formula and convince yourself that this is the function, or this is the expression which will take any basis vector to the Fourier transform. We can assume that we have access to Fg, and this should give us an HSP algorithm for G. With all the preparation, we are ready to solve HSP on G. Let's see how to do it. Notice that the technique I am going to show is similar to Simon's algorithm. This is generalization of Simon's algorithm, and similar technique will be even applied for Shor's algorithm. This technique, this procedure I am telling you is pretty standard and has been used in many cases. Let's see. The first step is to build the starting state. That is going to be 0, 0. First one is the group element, and second one is to contain the function value. I don't know how many function values are there, but definitely for the group element I should have at least these many qubits. I only need that the second register is big enough to hold all possible function values, and that will be given in the description of the oracle. The output of the oracle will go in the second register. The second step is creating equal superposition on the first register. That means we are going to query, we are preparing to query on every group element. This will change our state to this kind of an equal superposition. We have not touched the second register. Now we have prepared our state to query everything. Let's query. This will give us the function value in the second register. This is a highly entangled state. Notice that the second register's value depends on first register's value. And this is something which we have done umpteen number of times, specifically even in the Simon's algorithm. Once we have this, we can measure second register, and this will give us the coset states. That is going to happen because Fg is same for cosets. We will fall into some coset. There is a notation for this. I can call it GH, coset state, which is uniform superposition of all the things in the coset. This is called the coset state, and it is not going to matter which coset state we have. I will talk about this. Just the next step is going to be application of QFT over G. Once we have coset state, we apply QFT over G, and that gives us again this state, which is summation over all the characters, summation over elements of the group, and now this state can be simplified. It is easy to see that this state can be converted into another state where we will use the property that chi y of GH is chi y of G multiplied by chi y of H. And in that case, this chi y of G comes out, and in between I get this expression. I have just used this character property to taken out chi yg and summed up the rest of the things. And now if you look at this quantity is almost always 0. Why? Because we know that sum over any group G, a character is 0. A character of G is a character of H also. And hence this term will be non-zero only if chi y is a trivial character on H. That means at this point, if I look at state in equation 1, my amplitude is non-zero on y if and only if y was a trivial character on H. This tells us what should be our next step. Our next step should be to measure the first register. Measuring this will give us some character y such that y is trivial on H. Remember, this looks like L such that S dot L is equal to 0 in Simon's algorithm. Once we have gotten this, the strategy would be to repeat this step and get lots of such y's. What will this achieve? I will get y1, y2, yk, and we know that H is in kernel of yi. This is because of the property of y. After Fourier transform, we will remain in the superposition of only those characters which are trivial on H. That means if I measure, I will only get a character which is trivial on H. Another way to say it is my H will be a subset of the kernel of yi. Knowing this, classical post-processing would be just taking the intersection of these kernels. We will say that H is equal to intersection of kernel of yi. This will be the output. To make it work, we need to show after enough yi's, H is equal to intersection of these kernels. I will not complete this. You can look at Andrew Child's course notes for this. But this post-processing is very similar to what we did in the case of Simon's algorithm. And even this can be done for a general finite abelian group G. This works for any finite abelian group. The point was that QFT on coset states gives us characters which are trivial on H. And enough such characters allow us to find H. Few comments on this algorithm. One is that if you look at the state, this was the amplitude and chi yg was just a phase of this amplitude. In other words, the probability of getting a trivial character y actually was independent of which coset state I had. That is very interesting. This is saying that every character I will get with equal probability independent of whatever coset state I started with. When I do measure the second register, after measuring the second register, we get a coset state, and you might think that if we don't have a good coset, we might not have a good algorithm, but that is not the case. All coset states are equivalent for us. All of us will give a uniform y where y is a trivial character on H. It doesn't matter which coset state we started with. To summarize, QFT gives us the power to solve HSP on G. This works for any finite abelian G, and since we know how to do QFT on finite abelian G, we can say that we can solve HSP on any finite abelian group G. It is interesting to note that our techniques were very similar in the previous case also, and it's a good exercise for you to check that all these steps were done for in Simon's algorithm also, just that in Simon's algorithm we were looking at group Z2 to the power k. That's why this algorithm in some sense is the exact generalization of Simon's algorithm.